So some reactions are reversible, some chemical reactions. They can go forward and they can also go back. So we have two directions there, a forward direction, a rate of forward reaction, and the reverse, which also has a rate. And what we call in chemistry a dynamic equilibrium is where we have the forward reaction and the reverse reaction proceeding at the same rates. And so what we end up with then is a constant concentration of reactants and products. And so on the surface, it doesn't look like anything's changing. And yet, reactants are reacting to form products, and those products are basic, you could think of them as unreacting. They're reacting in the opposite direction. It's like the people at the airport. It's not always the same people, even though it may be the same number of people. So the forward reactions and reverse reactions are still occurring, but they're occurring at the same rate. And so the concentrations of the reactants and products don't change. And yet they're always changing. Yes?
Is there any energy loss, or could that go on indefinitely, forever?
It can go, I mean, not all reactions do this.
Mm-hmm.
But the reactions that do, yes, they'll go on indefinitely, just forever. Just running into each other and then coming apart again. Yeah. Any other questions?
I remember that you were saying that the actual ectothermic reaction comes from the bonds being reforged rather than being broken apart.
Yeah, when bonds are formed, energy is released.
So then if we were able to find what would be a major process that would be an infinite cycle of this? Of creation,
Well,
break apart, creation, break apart.
The thing is, it's not going to generate energy in doing that.
Because it has equal amount of force to break, right?
Right, because
Okay, so it's neutralized.
the energy that's being released by the bonds being formed is needed for the bonds to be broken.
So it's
And
probably
so, yeah,
an infinite cycle.
it's a good idea, but yeah, we can't do that. Okay, so let's look at this. Equilibrium, is this the right slide? Yes, it is, okay. Equilibrium is reached when the concentrations of reactants and products no longer change. So again, with this hydrogen and iodine reversible reaction. In the beginning, we have, and here's a little clock, so this is a timer. In the beginning, there are 8 hydrogen molecules and 8 iodine molecules and no hydrogen iodide. After 15 seconds, we have 6 hydrogens, 6 iodine, and 4 hydrogen iodide. So some reaction is occurring. At 30 seconds, we have 4 hydrogen, 4 iodine, and 8 hydrogen iodide. At 45 seconds, we have the same number. This indicates that we've reached equilibrium. So these guys are still moving around. We have 4 hydrogen and 4 iodine, and so this iodine could run into, well, these look like they're on a collision course right there. This hydrogen and iodine, if they run into each other with enough energy, they're going to form 2 hydrogen iodides. But 2 of the hydrogen iodides can also collide and reform hydrogen and iodine, and that's what happens. So we've got the reaction going in the forward direction and in the reverse direction at the same rate, but overall the concentrations of reactants and products don't change. Yes?
I understand the idea of the equilibrium part, but when it went from 6H2, 6I2, 4HI, and then down, wouldn't the reaction have slowed down because it kept constant, like on the chain?
The reaction, yeah. There was a change of 2 from 0 to 15 and a change of 2 from 15 to 30.
Yeah.
Yeah, it probably would be a little less because as the reactant concentrations go down, the rate will go down somewhat. So I don't think they were taking that into account.
But at this current moment between 30 and 45, we've reached a point where the breaking of bonds and creation has created an equilibrium.
Yes.
There are no further major reactions. We have no separate elements that are impacting each other, right? From the initial stage, like we had in 0.
We still have this reaction occurring.
They're being ripped apart and put back together sometimes.
Right.
Okay.
So we have some being We have some of these guys colliding and forming these guys, but we also have these guys colliding and forming those guys again. And, you know, sometimes it's a little hard to imagine, well, why would it do that?
This isn't a trapped chamber.
This is in a closed system, yes. Yep, closed system. So the concentrations of reactants and products don't change, but that does not mean that the concentrations are equal. So at this equilibrium state here, we have 4 hydrogens and 4 iodines and 8 hydrogen iodides. It's not the same number of each. And different equilibrium reactions will come to equilibrium at different points, and you can also influence where the equilibrium lies by adjusting temperature and pressure and different things like that. And so sometimes the equilibrium will be right in the middle, and sometimes it will lie far to the reactant side or far to the product side. And it can change, depending if the conditions change, but it doesn't always come in the middle. Yes?
So if it can change, they call it dynamic equilibrium. Is there any that can't change? Are there any that are always constant no matter what the temperature or pressure, or all the gases?
Well, some of them are definitely affected more by temperature and pressure, but most equilibria could be affected in one way or another.
So they're all dynamic?
Well, what it means by dynamic is that you have the forward reaction and the reverse reaction occurring at the same time. And all chemical equilibria do that.
Okay.
So here's a population analogy. Middle Earth and Narnia. It's like let's mix Lord of the Rings and the Chronicles of Narnia.
They would die.
The authors were good friends, though.
Well, yes, they were, but it's a funny illustration. I didn't come up with this one. I like my airport one, but whatever. It seems to me like there was more to that one. Is there another? No, that's it. Okay. Ooh, animation. It's like, oh, I hope I can find the animation. So here we've got initially a large population in Narnia, and there's very few people or creatures in Middle Earth. And so, it's getting kind of crowded, and there's new farmland and stuff over in Middle Earth and better hunting and whatever. So people are going to leave Narnia and migrate to Middle Earth and go over there and live. But now as things start to get crowded over there, if everybody moved over to Middle Earth, then they turn around and say, oh, look, Narnia is empty. I don't like these people. I'm going to go back over there. And then everybody gets the same idea, and they go back over there. Eventually, though, you've got people moving back and forth, but you have the same number of people on each side. And so you get a dynamic equilibrium. So you have people going one way and people going the other way, but overall you have the same, not the same number of people in Narnia and in Middle Earth necessarily, but the number of people in Narnia remains constant. And the number of people in Middle Earth remains constant because you've got 3 people coming this way per day and 3 people going that way, or whatever time period you choose. Do you like that analogy at all? Did it help at all? Yeah. I figured, they went to all the trouble to make the graphics, so, at least show it. Play animation.